Hello friends, I am Kumar Sir and we are at Galaxy Tutorials. Today we are looking at chapter number 12, Electricity 10 CBSE Science. Okay, chapter is very important. There are numericals, sums or problems, whatever you call coming in it. There are a lot of definitions. Okay, there are experiments. We will see the content because it comes in various sections of the paper. Okay, so electricity is very important in everyday life. You cannot imagine life without electricity. If our electricity goes for half an hour or 10 minutes, we feel so impatient. We start feeling depression. Our whole life today runs on electricity. So, first topic in our book is electric current and circuit. This is our first unit. What does this say? It is very clear. It says that in everyday life we are using some form of electricity. The book is giving example that we are generating electricity by the flow of water, hydroelectricity, and we are using a torch. In the torch, when we press the button, we complete the circuit and the lights or the bulb lights. Also, the book says that switch is the conducting unit. If the switch is put off, current will be off, torch will not work. Switch is on, current is on, and the torch will work. So the book says how to define an electric circuit. Electric circuit. The book says a continuous, no breaks, closed path. You may have a switch or whatever to close or open a gap. Path. Okay, so this is through which of course current flows is called an electric circuit. So continuous closed path, of course, for current, not the path you're walking on in a garden or something. Now, if you break this anywhere, for example, you turn off the switch, the current will not flow. Second point the book makes is current, conventional current flow and its error. Earlier we believed positive particles came out and went through the conductor, the path, continuous path as you've written, to generate the flow of electricity. As a result, every time we were showing current going from positive end of the battery or the source of power. Okay, today we do not agree with this because we know electrons flow. Technically, current should flow from the negative side. Electrons flow. This is correct. Okay. Now we cannot now go on changing so many textbooks because electricity is a very old topic. Modern research in it is not much. We have already done lots and lots of work on electricity. Okay, now we are going in electrons and subatomic particles. Okay, so we don't want to change everything that or confuse the world. So we stick by this. So we will accept this conventional current and we will never use this. Okay, does not make a difference to us because we know electrons flow because now we know the atomic theory, etc. But circuit always now is shown like this. So we don't call it an error, we have adapted to it. So conventional electric flow. What was there in the past? Second, what is current? What is current? Current is the flow of electrons through a conductor. Now, how do we define? We know it's a flow of current through the conductor. So we need formulas to calculate because we are having currents in various devices. Each device requires different current. Okay, my mobile requires a different current, or what you call amperes, than, for example, a fan or AC or a light or a TV. So current we have to define. So current is defined as I is Q upon T. Okay. Now I is the current through the cross section. So if I cut a conductor, and assuming it's a circle, that circular area I will get from that slice, how much charge, electric charge or electrons are flowing through it in how many seconds. This is how we are defining current. Okay, so we will have to write Q is the net charge which flows across the conductor, I is the current, and T is the time for which it is flowing. If you use electrical device whole day, air conditioner, you will have a huge bill. If you use it just for 15 minutes, you will have not much difference, a small bill. So the time is also important for which the current is flowing or you're using. That's number one. SI. Now the units for measurements are, okay, we are having units of measurement. Q is measured in coulombs. C. Okay, and it tells us that 1 coulomb is normally 6 into 10 raised to 18 electrons. Okay, then current is shown by amperes. We write A. Okay, and when the current is very small, for example, a watch or a mobile, we call it milliamperes. You know, millimeter, centimeter, units of conversion. So smaller unit. Then Ampere was a scientist on which, French scientist on which we have named this. So okay, so 1 ampere is 1 coulomb in 1 second. So if 1 coulomb charge flows in 1 second through the conductor, it will generate or use 1 ampere current. This is how to convert it to unit measurement. Okay, now we will see some example on this. We are looking at solved examples. We have a lot of examples which are there in the textbook, which have come in the past paper, and which are there in our practice sheet, sheet A, practice sheet B, assignment, past paper questions. So we will see which are there in the textbooks first. Okay, there are plenty of them for you to practice. Okay, the book says, example 12.1, page 200 of the textbook. A current of 0.5 ampere, I is 0.5 ampere, is drawn by a filament of an electric bulb. We are using a bulb. Okay, for 10 minutes. T is 10 minutes. Please remember, time should be in seconds. Never forget. So 10 minutes is 10 into 60, that is 600 seconds. Always keep them ready in units. Otherwise the sum will never come correct. So we are keeping it on for 10 minutes. Find the amount of electric charge which flows through the circuit. How much charge has flown through the circuit? Charge Q in terms of C. Now I have here I is Q upon T. So 0.5 is, I need to find Q, and I have 600 seconds. Therefore, Q is equal to 0.5 into 600. That is half of 600, or 5 upon 10 multiplied by 600, whichever way you like. This is 300 coulombs. Okay, Now you'll say, what a silly sum, very simple. 1 mark, can even ask for MCQ. So your formula number 1 for today is I is Q by T. You can change forms, bring I down, take T up. Don't learn so many different combinations, learn one formula. So we have seen formula number 1. Okay. How does a basic circuit look like? We have to see. Okay, so we have to draw a circuit diagram for that, and we will see how to draw a circuit diagram. And for that we need to know certain symbols for the circuit diagram. So we will go to them. Okay. Page number 203 of the textbook shows you symbols, standard symbols. We cannot change the symbols. Okay, the symbol have to be used, they're standardized across the world. So first, a cell, electric cell, not a jail cell, electric cell. We are showing it in a positive and a negative. Positive and a negative like this. This is your battery, electric source, whatever. If I require more than one cell, I will have battery, electric battery. So this will have many cells like this, plus minus, like how you put 2 in your remote, TV remote, etc. Third, plug key. Plug key. Plug, earlier we used to call it plug key, now we call it switch. Plug key. Better word today is switch. We switch it on, we switch it close. So open is like this. This is open and this is closed. Means it is occupying and it is conducting now across. Okay, we are purposely not making that bigger in the center because it looks untidy. It is touching everything. So you just like you put a conductor inside, so the 2 plates are now touching. Third, a wire joint. We may have to join circuits, like one is going to the fan. From that I have removed something for the tube light. So we are showing joints by a small dot circle. This means a joint. Then if a wire crossing. So I have one wire going like this, I have another wire lying like this. In circuit, I will show them like this. A jump is shown. It is not joint, it is lying on top. So it has nothing to do with the wire below. Then, so they don't join. Joint will always be by that black dot. Bulb, electric bulb, is shown by a symbol like a heart. This is the symbol for a bulb. And resistor. Resistor is any device which prevents the flow of current. Such a big thing, resistor. You are using it every day. You are turning the volume up, you are turning the volume down. When you are turning the volume down, resistance increases, flow is less, sound is less. Fan, you got numbers on it, 0, 1, 2, 3. So when you take it to number 3, fan is fastest. You bring it to 1, slowest, and 0 it stops because the resistance goes on increasing. At 0 the circuit is broken. So fan will not at all run. Resistor is shown by a crooked line in the conductor. Okay. Resistor which can change is called variable resistor or rheostat. This is same, only thing we get an arrow, so that means I can switch on and off, slide like 110 volts, 220 volts, or fan 0, 1, 2, 3. You are varying the resistors, and fixed resistors are already there in your circuit, mobile, etc. So when you put the electric bulb for a charger, the phone should not melt, more current should not flow. Those are fixed resistors. Fuse, we will see, is a fixed resistor. Then we have an ammeter. This will help us to measure amps or the current. This is shown by a circle with a A written on it. Okay, so two eyes are coming out of it. One on the positive side, one on the negative side to measure. And if you have to measure how strong, we have to measure volts, the pressure, the potential difference. In this case, we will have V. In this case, we will have V. And we will show plus and minus current flows. They are not attached in the same manner. We will see when we come to them. So once we know these symbols, my friend, we can draw electric circuit. So we will see a simple circuit now, how to draw. Yeah, so have a look. Cell, more than one cell battery. To switch on and switch off, we have plug or a key or a switch, open, closed. We have joints, if we need current to go to somewhere else also. We have crossing. Wire are just lying on one top of the other. They are insulated. They don't touch technically each other for passage of current. Bulb, resistor, wavy line, variable resistor with an arrow on the wave so that we know it can move in front or back. Ammeter, circle with a A, voltmeter, circle with a V. Okay, so we'll go forwards. Since we have seen the symbols, we will go back and see the circuit. So figure 12.1 in your textbook on page number 200 is showing you a circuit. What does it show? It shows a bulb in a circuit and an ammeter to measure how much current is flowing. It shows a key. Of course, the key has to be closed for passing the current. And it shows a battery. Okay, so this is how it shows a simple circuit. And current is flowing, as I told you before, conventional. So it will flow from positive to the negative. In reality, it should be opposite. Okay, this is plus, this is minus. Key is shown by K, ammeter by A, device will be here. That's like a resistor because it is using current, and battery will be, cell will be here. So this is how a simple circuit. One mark, draw an electric circuit for using cell, electric bulb, ammeter and plug key. They may ask you to use anything. Everything has to be in a continuous path. This is fixed. This is what will be told by voltmeter, ammeter. How to add voltmeter? Please wait. We will see. Okay, so this is how electric circuit is drawn technically. Okay, we will move forward. Yeah. Next, our text talks of electric potential and potential difference. My friends, when we touch a battery or a cell, we don't get thrown off, shock, burning. We handle cells in our hand every day. But if you happen to touch an electric wire, or you try to put a nail or a metal device into one of the sockets, okay, carrying current on the switchboard, you will immediately be feeling the electric current. If you touch both the ends, you will be pulled. If you touch one end, you will be thrown. Okay, but you will feel the current flowing through your body because your feet are on the ground and you are getting earth. Your body contains salt solution, ions in your plasma, cellular fluid, and that is how you are a conductor. Okay, if of course you are wearing thick rubber boots or you're standing on a rubber mat or on a wooden big piece, then you will feel very mild, like somebody touching the hairs on your hand, goosebump like thing. Otherwise, when you conduct, dangerous. Okay, and if you touch both the sockets, plus and the minus, you're wearing rubber, you're wearing whatever, be sure you're going to heaven. Okay? So, there is so much force which throws off, and there's so much force which pulls us also. Okay? So, this flow is the flow of electrons is because of the pressure. It is called, in physics, we don't say pressure and all, because pressure is normally associated with mechanical device. Electric potential. And potential difference. We have already seen, my friend, we are measuring this in volts and the unit is V. Volta was the scientist. Okay, so we are seeing. Now, we have got at your home, you got one socket hole here and two socket here. And every device minimum has two wires, if not three. The third is neutral. It goes directly to the earth. It's called earthing. You have been told that we should use a 3-pin. But the two are important. In olden times when we never knew earthing much, or at home at least we not to earth because wires were expensive. So we used to use two wires. Today also many things, those minor things we use, a bulb, a small heater for the pain of your body, etc. have two wires. Computer things have two wires. CPU will have three wires. If it's delicate, it's expensive, then we'll use three wires. In this, we have got electric potential. The difference between the two is 0 and 220. 0 volts, 220 volts. Because this is going finally to the 0 wire, which will finally go to the earth. Earth at the station. And your bypass, suppose wire breaks, we also have another wire which your electrician will connect it to the earthing plate in your building or home at the ground floor. We make a pit hole, put coal, put sand and put salt, put water, make a solution, and then we concretize it with this plate inside and wire going down. So immediately, because of the ions, it will conduct and the current will go away and save your life in case one of the wire, that is a negative wire, broke and the current flows through your body. Now it will flow down. So you will only feel that somebody is touching a hand. So you know leakage is there. Now this difference is the potential difference. And this is the electric potential. It is capable of giving you 220 volts. Okay. So how do we define volts? We define potential difference between 2 points in an electric circuit carrying current as work done, okay, to move a unit charge, okay. So the work means the push which you're doing, hard work, to move the unit charge from one point to another. From one point to another. This is how we define potential difference. Okay? PD shortcut. So we are imagining I am at point A, I am going to point B, and I am taking one electron, one charge. Of course, conventional we write positive, does not make a difference. So one movement. Okay? How much work I need to do is my potential difference. Now, since the electric supplying company is quite far, you're generating electricity at Powai, Tarapur, other states. By the time it comes here, the wire is too long, weather, condition of the wire, etc., and supply of current. That current charge will go on, will have more opposition, will go on decreasing. That is why we supply higher voltage. At higher voltage, leakage loss is less. At lower voltage, leakage or loss is more. So you cannot touch 440 volts or near a local train. They tell you never climb up 25,000 volts, okay, 44,000 volts, big cables of electric company come to your building. So at a home, it is regulated through a small transformer at the end of the lane or at the end, and that will bring it down to 220 before it comes to your house. In very developed countries like America, 110 volts is supplied inside. so that people don't die of shock. Now, why the hell are we using 220 to die? This is because the electric system was established in India by the British. We were a colony of the British. Now it is impossible to change so much electricity. They were the first to start trains and electrocytes. Okay, so we are stuck with 220 volts. And as you can see, 110 volts is half, so damage is lesser. Okay, so V is W upon Q, work done upon charge. Okay, again I write here W. We have written everybody, we didn't write W. W is the work done in transferring a charge. Okay, and V is the potential difference. So formula number 2 I'm putting here, V is W by Q. Keep track. Now, unit of V is volt, named as I told you after volta, SI unit. So 1 volt is when you take the potential difference between 2 points in a circuit which carry in a conductor, when 1 joule of work is done to move 1 coulomb charge. 1 joule work is measured in joules. We will see that also. We need in the last parts, work done by electric current. And Q we already know is measured in coulombs. We keep reminding so that you keep remembering. Okay, so 1 volt technically is 1 joule upon 1 coulomb, and it is written -1. This system you already know in laws of motion. In your lower standards, we write S minus 2 meters per second. Okay, or meter per second square. Now, let us see a numerical on this. 12.2 on page number 202 in your textbook says how much work is done. How much work is done? In moving a charge of 2 coulombs, we are moving a charge of 2 coulombs, okay, across 2 points having a potential difference, okay, PD, okay, which we now decided to use V, simpler, is 12 volts. PD, pressure difference, no, so that's why we write V, electric pressure, okay. So we will use the formula. We have a formula. V is W upon Q. V is 12. W we don't know. Q is 2. Work done is 24 joules. This is how we will do the sum. 1 mark or MCQ. Please have a look. Okay. So we have done till 12.3. We saw circuits, we saw volts, we saw amperes. So we will move forward with certain law. Okay, so let's see. The book starts with the unit Ohm's law. So fourth part in the book is Ohm's law. Ohm was a scientist who studied the flow of current under different voltages. He made a table as you do in your graph plotting, and he saw at how does the current flow. Is there some proportion? Is there ratio? If I double the volt, does the current double? He did a test experiment and he made an Ohm's law. Okay. Now, German physicist George Simon Ohm. Ohm says that both are related. The current and the volts are related till a certain level. After that, your conductor will melt because your current conductor cannot go on taking unlimited because heat will be generated because there is some resistance in the conductor. Or your conductor has to become thicker and thicker. The wire in your mobile and all is just like some hair or a mustache wire. You can see wire which is coming in your home is slightly more harder, but see the wire, overhead wire of a local train. You will see it is a 2-inch diameter wire. And if you see the cables which come, there are so many such wires in one big bundle. Okay, so we have to overcome, otherwise they will melt. So Ohm found out that if you plot a graph, okay, of potential difference against current, you get a straight line. No voltage, no current, okay, and they go on increasing linearly. So there is a linear proportion between the two. Of course, when it will melt, the graph will go. We do not draw. We only draw it to that stage. Okay, we are not negative people. Okay, so he said potential difference and current are directly related. Now, by maths, we call such a thing K is the constant. To convert proportion into equality, we use a constant. Now, K is maths. We use R. In physics, same thing. R is the resistance. What is lost? So you can see here that my ideal will be when both are equal. So there is least loss. We'll be near that. We can't be ideal. There is some resistance in the wire. Maybe as impurity, maybe how the metal has been packed, etc. And thirdly, there are protons, there is nucleus, there is bound to be some resistance in the conductor. So this gives us V is IR as Ohm's law. Voltage is current into resistance. Okay, so one resistance is measured in ohms, and the symbol of ohm is like this, Greek alphabet omega. Okay, so we are having from this formula R is V upon I. So 1 ohm is 1 volt on 1 ampere. Okay, from this you can also do I is equal to, by converse, you can move everybody down. I can get 1 I here, I can get 1 omega here. So you can go on switching, does not make a difference. So third I'm putting is V is IR. R is the resistance. Okay. Now this resistance gives us peculiar problems. What does the resistance depend on? Which wire I should use at home? Better the conductor is one which will give electrons easily. Flow, not give up, flow through it. Now gold is extremely good. So I suggest to you, do gold wiring in your home. If it is possible, tell me. I will also do. Now you'll say, the cost is so much. If you put silver, second substitute, very good. But night we will sleep, morning those wires will be missing. So that is why we settled for copper, the third best. Now copper is getting expensive day by day. As a result, people have started using aluminium in the wires. So one of the wires is copper. They'll say connect the positive to the copper, to the other earthing and negative wire, take aluminium wires. The problem with aluminium wires is it is a good conductor, but it is brittle. If you bend aluminium 2-3 times, it will break. Copper is quite malleable, so you will bend in the house, circuits, etc. They have never much broken unless they are impure. Okay, so we will have to know the material you are giving me. Now you will say use iron. Iron conduction is low, resistance is high, but is the cheapest. Okay, that is why whenever there are weddings or anything in the lane, on the road, people first put iron wires on the top and then loop it with these small copper wires of bulb series, the laddies, and then you see them decorative lights. Now for them, stretching long copper wire is expensive, it may break, they will need thicker, so they use electric wires on the pole on top. And from them, currents plus and minus, iron wires, from them all the electrical decorations are hung. So what does, first it depends of course on the metal as I explained to you. Second, the length. Smaller the wire, less will be the resistance, of course, because the path is less. You are banging against less things. You are reaching fast. If my home is near my school, I'm so happy. In 5 minutes, I'm home. But if I have to travel 1 hour to travel from my school to home, I get tired of the way only. I can't study when I reach home. Third, if I have a big gate like school, we find that all of us run into the school. But when I come home, we normally come one by one or maximum 2 people at the same time because the gate is small. If the diameter of the conductor is large, current will flow easily. That means thicker the conductor, less the resistance. Thinner the conductor, more the resistance. That is why we cannot take very thin wires like mobile wire and connect it to electric currents in our house. These wires will melt. For battery, 5 volts, 10 volts, it is okay. Where it is taking the power, they have got thick iron pins which you put in the socket. So that is why we will see resistance is proportional to the length of the conductor. Resistance is proportional to 1 upon the cross section. The diameter, we have to assume it is circle for easy calculations. Now combining both, resistance is proportional to L by A. And as we did before, we'll put a constant to make it equal. So we use resistance is equal to rho into L upon A. Okay, this is how we do. Rho is the constant of proportionality and it is called the electrical resistivity. Electrical resistivity. The property of that metal, the packing of the atoms in that metal, which you can't change. Each has its own resistivity. Okay. So this is how they are related. Table 12.2 for match the column. Table 12.2 is a resistivity table. Please go through it and see. Conductors, resistance is given in ohms. Resistivity is given in ohms. And alloys are poor. Okay, we see. But they do not oxidize easily at high temperature. So that is why we use them in electric heating device like iron, toasters, etc. and fuse. And third, insulators do not conduct much at all. Glass, rubber, ebonite, diamond, paper. Please look at the decreasing values or for your exam so that when 3 values are given to you and you are asked from these 3, which is a conductor, which is an insulator, and which is in between, please learn to see the table. We do not have to memorize those values. Okay? Values are given, we are supposed to see higher, lower, and middle. So, we will look at problem 12.3 in the textbook, page number 208. What does it say? How much current will an electric bulb draw? How much current will an electric bulb draw? From a 220 volts. Okay. Source. If the resistance of the bulb filament is 1200 ohms. That is the first part. We will look at this first. Now, as you can see, we have got a formula there. V is equal to IR. V is 220, I don't know, and R is 1200 ohms. So I is equal to 220 divided by 1200. Yes, my friends. So have a look. When you divide, cancel 0, divide by 2 and all, you will get 0.18 amperes as the answer. This was part A. I will write A here. Sum is not over. 2 marks. Another part is there. How much current will an electric heater coil? I have a heater at home to warm the water. And from 220 volt source, if the resistance of the heater coil is 100 ohms. Now I'm supposed to find how much current, amperes, will my heater with volts 220, that is standard, at a home everybody gets 220 volts, okay, and resistance is 100 ohms. Now the bulb, you see, had 1200 ohms. Why? More the resistance, the wire gets hot, wire glows, and the bulb gives out light and heat. But heater, I don't need light coming out from my heater. So you see, that is the difference. So when I heat it or take a metal like tungsten or nichrome, 1200 resistance, I will get light, white light coming out. And of course, I can put colored glass and all and make it color. So here I see V is equal to IR. Again, we will always write the formula. V is 220. I have to find, and R is 100. So 220 upon 100 is I. Now, when you divide this, you will get 2.2 amperes. So, you see, because it is a heater, 2.2 bill will be more amperes are getting used. So, if I have a bulb in my house and I have a heater in my house, the heater will take more energy and the bill will be more. That's why we don't keep heaters switched on whole day, except in cold countries where you have no choice. So this is 12.3 on page number 208. We will look at another sum, 12.4. On page number 208 of your textbook says the potential difference between the terminals of an electric heater is 60 volts, okay, when it draws. So first, always read and write simultaneously. Is 60 volts when it draws a current of 4 amperes. From the source. What current will the heater draw? What current will the heater draw? When the potential difference is increased to 120 volts. So if I double the voltage, how much current will be used? Okay, first, R is V upon I. I don't have value here, I have both the values here. Now the heater is not changed. The resistance of the heater will not change. So once I find R, I can use the R for the second part because they have not given me R. So this is 60 upon 4. As you can see, you have 15 ohms. Now here I have already R as 15 ohms brought here. V is IR. When I make it 120, I do not know the current, but I know my resistance is 15. So 120 upon 15 is I, which when you divide, you will get 8 amperes. Okay? So this is doubled, this also doubles. They are directly related. So this you should remember. I'll put it here. V increases by a ratio, I also increases by that ratio for your MCQs and objective. We don't have to sit to calculate. For the same conductor, resistance should not change. Now instead of heater, I use a bulb or something, then resistances are not same. Two appliances can't have the same resistance. But a similar copper wire of same diameter, resistance will be same. Keep track of this. We will look at the fifth sum. In the fifth sum of the textbook, 12.5, on page number 208, I have resistance of a metal wire of length 1 meter, length is 1 meter, is 26 degrees. Resistance is 26 ohms, sorry. Resistance is given at 20 degrees centigrade. Temperature is given. If the diameter of the wire is 0.3 millimeter, what will be the resistivity of the wire? Rho will be how much? Okay. Using the table which I told you earlier, where values are written, predict whether the material is good conductor, bad conductor, insulator. We have to find out. Now, in this case, length is 1 meter, extremely nice. Resistance is 26 ohm, excellent. Diameter is millimeter. I have to do MKS or SI units. Millimeter is CGS or lower units. So I will get 3 into 10 raised to minus 4 meters, or 0.3 meters divided by 1000 to make it meters. Then length standard, resistance standard. Why did they give me temperature? Okay, just for fun. If the temperature changed, we would have thought temperature not change. So extra data given to confuse you. Now we have in our formula, R is rho L upon A in our formula. 26 is equal to rho into L is 1, and I have diameter and I am supposed to see the area. Okay, so in this case we will be using the area as pi r square, so area is pi r square. Geometry we have to do. Okay, area of the conductor, the wire, circle. So area is pi r square. That is pi diameter upon 2 square. That is pi d square upon 4. That is how I get the area. Okay, so we will have to find the area and put it in this formula. This is rho into length, and here I have pi d square divided by 4. You see, as simple as that. Now when we substitute the values which are given now, pi is 22 upon 7 and all, I get rho in this case when I substitute. So 1 upon 3.14 into d is 3 into 10 raised to minus 4 square. Okay, this is d square is divided by 4. Or even if you will take it like this, it is pi d square, so it will not make a difference. When I solve this, and rho will now also be 26 also will come down, I will get rho as 1.84 into 10 raised to minus 6 ohms per meter. Ohms meter, not per meter, ohms meter. Now, you see from the table given to you, this is shown as manganese. So the material I am using is manganese. Okay, so that is how a table works. Let's see 6 sum. Sum number 6, 12.6, page number 209 of your textbook. Okay. It says, a wire of a given material having length L, length is L meters, and area of cross section A, area is A meter square, has a resistance of 4 ohms. Resistance is 4 ohms. What would be the resistance of another wire? I have another wire, I want to find the resistance in ohms. Okay, of the same material. So resistivity is same, rho is same. Having length L by 2, I am having half the length. and area of the cross section is doubled. Okay, L1, A1, L2, A2 is doubled the previous. Yes, my friends. So for the first wire, this is wire 1, this is wire 2. We are having a look. For the first wire, R1 is materially same, so there is no R1, R2, but I can still put, because we have taken two cases. R1 is rho L by A, and when I substitute these values, you will see this is 4 ohms given. Correct? Now for the second wire, I've just substituted, done nothing in the first case. Let's see the second wire. R2 is equal to rho, because the metal is same, L by 2 and 2A. Okay? Now when you solve L by 2 upon 2A, you will get, okay, you will see this will become 1 upon 4 rho L by A. So this, my friends, is R1. This, my friend, R2. And this is 1 by 4. No need to solve further. So you will see the resistance of the wire now. You can see 1/4 into R1. R1 was 4. Is 1 ohm. That is how to do the sums. Wire, 1, 2. Length halved, area you can see doubled. Resistance given, resistance depends, so material resistivity is same, resistance won't be same. So first, we are using the resistance, we have the formula. Second, we put and substitute this part, we will get like this. So numerical less, analytical more. That is how we are supposed to solve. Okay? This is where we will stop here today. Okay? Thank you.